Okay, in this video I am going to walk you through acid-base reactions, okay? So first off, we're going to start with some pretty simple terminology, and then we're going to get to some pretty heavy-duty examples towards the end. Now, some definitions. We do need to define acid-base acids and bases. The first one is going to be Arrhenius, who studied ions. His definition of an acid is that it produces hydrogen ion when dissolved in water. His definition of a base is that it produces hydroxide, okay, and this is the most common one. Now, as chemists went on, we had to kind of expand some definitions because we found that chemicals behave like acids and bases, but they didn't always fall into these categories. So the next one that came along was Bronsted-Lowry. Bronsted-Lowry is an acid is a hydrogen ion or a proton donor. Remember, a hydrogen ion is essentially a proton floating around, because if you have a original hydrogen atom, let's say with just one proton in the middle and one electron, well, if it gives away that electron, it essentially is just left with a proton floating around in space. So that's why you'll hear it defined both ways. A base then is simply going to be that proton acceptor. So we're just dealing with the hydrogen ion transfer for these. Now, another definition set that is out there that you guys are not responsible for is Lewis. Lewis acids and bases is a broader definition. It has to deal with electron pair transfers, but that's beyond the scope of what we're going to cover. It is out there, but we're not going to be responsible for it at this point. And since water is a non-electrolyte, the amounts of hydrogen and hydroxide cannot exist in solution without combining. So pretty much we can use water as this, pool or reservoir of where hydrogen ion and hydroxide ions will actually combine and then recombine. So that's why a lot of times you'll see us write water as HOH, because we can think of them as splitting off. They will actually self-ionize into hydroxide and hydrogen ion, and then they'll reform again as quickly as they separate. So, okay, a couple of other terms that we need to be familiar with. Here's again is our Arrhenius acid. This is just showing you that this is the general term we'll use. Hydrogen ion will be transported. Now, the reality of it is a lot of times we will write hydrogen ion, but the better terminology, not necessarily better, but the way the AP will say it, is that what really happens is that when you have that hydrogen ion floating around in solution, it actually will attach to a water molecule and make a hydronium ion. Okay, so the take-home message needs to be, because AP will use the hydronium ion, but when you see hydrogen ion, also think of it as hydronium. So just the FYI, we want to get that in our memory banks. And then you also will have whatever anion is left over. Okay. Now, with what are called monoprotic acids, this is when only one hydrogen ion is given off per mole. Okay, and this is going to be really important. We've talked about ion concentrations and how that will change. So hydrochloric acid has one acidic proton or one hydrogen ion, and mono means one, so that's where we get that from. And this is just the chemistry that would take place. If you take hydrochloric acid, which is an acid, you combine it with sodium hydroxide, which is a base, we form water and salt. Our net ionics for a lot of strong acid, strong base reactions, no, you're not going to lose the hydrogen. You're going to keep that one. What you are going to lose, for spectators rather, is going to be your chloride. Is going to be your chloride and your sodium. So the net ionic reactions for a lot of strong acid, strong base reactions are simply hydroxide plus hydrogen gives us water. Di means two. Technically poly means many, so anytime you get more than one can technically be a polyprotic acid. Diprotic is specific to two. Phosphoric, you get 3 hydrogen ions, which the reality of it is we're going to talk about how likely these are to really split off or not when we get more into weak acids and weak bases next semester. So our strong acids, if you remember, we just need to have these memorized. These are ones that will completely ionize. Okay, everything else is a weak acid, which means we keep it together in a molecular reaction, or it will not completely ionize. Okay, strong bases are going to be our metal hydroxides, especially group 1s and group 2s. They will completely dissociate things like sodium hydroxide, potassium hydroxide. Those are our group 1, group 2 metal hydroxides that will react. Okay, neutralization reactions are typically metathesis, the easy metathesis ones, otherwise known as double replacement or displacement, where you get an ion transfer as opposed to a redox reaction. It, like I said, typically involves ion transfer, and it most likely involves the reaction of hydrogen ion or hydronium, so we want to get that into our heads that they're really the same thing, and hydroxide to form water. And that's typically your most common strong acid and strong base reaction. Weak acids and weak bases are when we're going to more focus on the Bronsted-Lowry definition. So again, here's our Arrhenius acid-base reaction or neutralization. You get an acid and a base to form water and a salt, which from our standpoint is just an ionic compound. Okay, is what we're going for on that one. And this is just general. M stands for metal. A stands for anion. So over here you get your metal and your anion. So it's just generic versions that you will occasionally see us use. Again, a salt is an ionic compound formed from the anion of an acid and the cation from the base, which is typically a metal. Okay, titrations. Titrations are volumetric analysis. It's a technique used to find the amount of certain substance by doing a titration. We had all at least seen this last year. Potentially use the Bureys, we'll use them this year. A titration is when you add a certain volume of a solution with a known concentration to a certain amount of solution being analyzed, which is an analyte, or an analyte. Now sometimes you can use M1V1 equals M2V2, and that's when it's a 1-to-1 ratio and it makes us happy. I'm going to show you the dimensional analysis way today, and then we can always understand that this is a shortcut a little bit later. Okay, so again, just some definitions here. Now your equivalence point, really important, is when there are equal moles of each reaction present, and an indicator, this is what's different, okay? We don't have our typical bubbles or energy released as heat or light and to let us know that a reaction, so what we have to do is add an indicator that will change color near the equivalence point. And these typically change color based on the presence of either something being acidic or basic, and we'll take a look at a couple of these to show you what they look like. And the endpoint is when the indicator changes color. So essentially what you're trying to figure out is to know when your reaction is going to be done, and then you have an indicator that's going to show us that that changed place, or that reaction took place. So for example, okay, a good titration, you have to know the reaction, the equivalence point must be marked accurately, and you need to know the volume of the titrant needed. Okay, so you need to know some background information. Now, one really common one that we'll use is phenolphthalein. Phenolphthalein is a very common indicator. It's clear until all of the acid is consumed. 1 drop of the excess base will turn it pink. So as soon as we have extra hydroxide, it turns pink, and it lets us know that. So for example, let me just show you what a typical titration. We do a lot of titrations with sodium hydroxide because there's 1 molecule of hydroxide. It makes the math easy. And you'll typically have an Erlenmeyer flask that may have some type of acid. And so a lot of times what will happen is you will know your molarity of sodium hydroxide, so let's say it's 1.0 molar, and you may know that you had to add, okay, so we added, drop, let's say 28 milliliters until it turned pink. So as soon as it turned pink, it means the reaction is over, there was too much hydroxide to be added, and so then the reaction was done. Now what you will also know a lot of times you'll know, let's say you had 50 mils down here, and so what you'd be searching for would be the molarity of this solution. Okay, and that's a very typical titration. But ultimately, instead of using a gravimetrical analysis or mass procedure, we have to use a volumetric procedure. And I'll probably do a quick demo just to show you what this looks like. And then we're going to do a couple of labs with titrations, which again will hopefully make it make more sense. So, okay, really important. We're going to flash those.